Okay, the gradient. So definition, the vector df to dx, df to dy is called the gradient of f. So this is for a scalar function of two variables. If it's three variables, it's going to be df to dx, df to dy, df to dz. Okay? So we have a lot of things to say about it. Let's first say that it's denoted either grad of f, or, and I'm usually going to use the other notation, or this upside down triangle thing of f, often written with an arrow to indicate that it's a vector. Okay? It's a vector. It has components. If f is a two-variable function, the gradient is going to have two components. Clear? Good? Okay. And the first thing that's important to realize is that it's defined at any point. Okay? So when I just write this, remember that df to dx is itself a function of two variables. Remember that? We saw it in examples. So this can have x's and y's in it, and this can have x's and y's in it, right? And when you evaluate it at a given point, you get a number, right? df to dx at the point x0, y0 is a number, and df to dy at the point x0, y0 is a number, okay? So this thing, for any x0, y0, you get a number, df to dx at x0, y0, and df to dy at x0, y0. Clear? So actually, what's going on here is, if you think about it for a minute, you take a function, f, it's a two-variable function, take a point, x0, y0, points are, we think of points as vectors and vice versa, right? So take a vector, x0, y0, take a function, you get a new vector, df to dx at x0, y0, df to dy at x0, y0, okay? So this is the first remark that I'm going to write, and tell me if you agree. Remark: the gradient of f is itself a function from R2 to R2, or R3 to R3 if f is a function of three variables. Okay, why? It takes a point x0, y0 and sends it to the gradient of f at that point, which is df to dx at x0, y0, comma, df to dy at x0, y0. Do you know this notation where you write an arrow with this small line at its origin? Do you know this notation? So this notation stands for, usually for functions we write the function and then the domain and the range, right? The notation on top you all know, right? This notation indicates what the function does. For a given point in the domain, it sends it to a given point in the range. Do you see that? Okay, clear, everybody? So we haven't encountered yet functions like this. Functions where both the domain and the range are not single variable. Okay? So this is our first example. The gradient is not a scalar function, right? A scalar function satisfies that the range is R. That's why it's called a scalar function. We also saw functions where the domain is R. Those were curves. Remember? Curves, the domain was R. Those were the t's. And the range was x of t, y of t, or x of t, y of t, z of t. R2 or R3. But the gradient is a function, a vector-valued function. Okay, let's maybe write that. Okay, so it sends vectors to vectors. Okay, it's a vector valued function. Okay, it sends vectors to vectors. So it's no longer a scalar function. And it's called, not just the gradient, all these functions where from R in general, from Rm to Rn, functions like these are called fields. That's what they're called. And why are they called fields? There's even a picturesque reason for these things being called fields. Think what it does. You look at let's look at the plane, because we took the example our example was for functions of two variables. So take a point x0, y0. Here's the point x0, y0. Plug it into the gradient. What do you get? You get a vector, right? Do you see that? And this vector, let me draw it like this. So at every point, you get a little vector like this. That's the gradient of f at the point x0, y0. Okay? Now take another point. Maybe here, you get a vector. At every point, you get a vector. Do you agree? At every point, in R2, the function spits out a vector. Right? And do you see this nice field, okay, of grass? Okay, that's precisely the reason. It may sound, I don't know, but that's really the reason why it's called a field. Okay? Good? I mean, if I were a cow, this would look very tasty to me. Okay. Everybody good? Understand the idea? Okay, good. We're going to discuss fields, vector-valued functions, in detail, in a lot of detail, as the course progresses. Okay. The first field we're encountering is the gradient, and our treatment of it at first is not going to be a general treatment of fields. Okay, we'll get to that later. This is just kind of a, hey, we've met vector-valued functions. Okay, good. Here's another remark. Remember, so we discussed directional derivatives, and for directional's derivative, we had a theorem that said if f is c1, then the directional derivative with respect to u, df to du, equals df to dx times u1 plus df to dy times u2. Remember this theorem? Everybody? I want to rephrase. Okay, so this theorem, remark, the theorem, this theorem, can now be rewritten, as f is in C1, or f is differentiable, implies df to du equals, these two are precisely the components of the gradient. These two are precisely the components of u. So do you agree that what's written there is precisely the gradient of f dot the vector u? The scalar product of the two vectors. Does everybody see that? Good? The gradient is df to dx and df to dy. U is u1 times u comma u2. Their dot product is precisely this. Good, everybody? Okay. So that's this theorem. Just getting used to the notation. By the way, the notation, remarks regarding the notation. So this is, as opposing to many symbols we use, it's not a specific letter in any specific alphabet. So what is it? Where is this letter from? Or this symbol from? So the answer is, this thing, so let's maybe write it as a third remark. this thing is called, we're going to use it a lot in this course. It has, it shows in various notions, not just the gradient, is called nabla. Nabla. And it has an interesting story. So the person who introduced it, if I remember correctly, is Maxwell. The same Maxwell from the Maxwell equations in physics. And he needed some notation like this, and he said, okay, well, we have delta. Remember, this is delta. This is the Greek letter D, right? Anybody here from Greece? Or from any Greek-speaking country? Cyprus, I don't know. Okay, so this is the Greek D called delta. And he said, okay, let's turn it upside down and call it atled. That was his suggestion, and the mathematical or physics community said, come on, this is we're serious people. No way. Okay? And then I don't remember who suggested, or maybe it was Maxwell that said, I don't remember, but this was not accepted, and instead they found a different name for it, and nabla is the Greek word for harp. Why harp? Because I even practiced a bit. Right? This is a harp. Huh? And in fact, that Greek word for harp, I don't know which one precedes the other. I in fact think that the Greek word for harp, nabla, was preceded by the Hebrew word for harp, which is nevel. Okay, I'm quite sure that nevel came first. Okay, so that's the origin of this word for this notation. And can you picture King David playing his harp for the sheep or whatever? Okay, so it's called nabla, which is Greek or Hebrew for harp. Okay. In fact, the notation is also sometimes called del, and del is Persian for heart. Somewhat. Okay, but anyway. Okay, good. I want to focus on this thing. Okay, our first, this new thing that we just introduced, the gradient, has a very useful geometric meaning. Okay, and that geometric meaning is going to stem from this property. Okay, so let's write that. So let me rewrite it. df to du equals the gradient of f dot u. U is a unit vector. Now, suppose you're walking along a trail, okay, on the mountains. So remember our topographical maps for describing graphs of scalar functions, remember? And we had those level curves. Remember all that? Okay. So you're walking along a trail, and natural questions that arise are, for example, where to set the trail. Suppose you're the one, or a road. You're the one constructing a road. Where would you want the road to be when you're driving along the hills? You wouldn't want to drive along the hills like this, right? You would want to go around along level curves. Do you agree? Right? What is a level curve? A point on a level curve, the direction of that level curve is precisely the direction in which the directional derivative is zero. Does everybody agree to that? A level curve is a line or a curve along which the points have a fixed value under f. Do you agree? So f at every point along the level curve is fixed. It's some constant. Okay? So when you drive along a level curve, the direction you take, you turn right or you turn left because you want to stay along, you don't want slopes. Do you agree? You want the slope to be zero in whatever direction you're driving, and saying that the slope in that direction is zero is precisely saying that the directional derivative in that direction is zero. Does everybody see that? Okay. On the other hand, you may be a very an athlete, okay, and one that really has to and you want to get to the top of the hill, and you want to do it in the steepest available route, okay? So a natural question would be, here's the top of the mountain up there, the summit. You want to go to the summit in the quickest direction, quickest in terms of steepest, the fastest way up, okay? Shortest in terms of distance, okay? Not necessarily in terms of time. Okay, so that would be asking a different question. In which direction is the directional derivative the biggest? In which direction? There are many directions. If that's the summit and this is the level curve, so along this direction, the directional derivative is 0. We're on a level curve. That's where we came from. So in this direction, it would be 0 as well. In this direction, the directional derivative is maximal. That's the quickest way to the summit. Okay? And if you're just a ball rolling downhill, you would of course go in the steepest direction downwards, right? That would be in this direction where the directional derivative is maximal negative. Do you agree? So this directional derivative measures slopes along various directions as we... Clear? Is that clear? Good? Now, calculating directional derivatives, you have to know the direction in order to calculate the directional derivative, right? But trying to explore where the directional derivatives are maximal or minimal, you can do just when you know the gradient. And knowing the gradient is calculating two things alone, df to dx and df to dy. Okay? So let me write all that and tell me if you agree. So there are going to be 3 facts here. The first fact is, if, or let's write it like this. The directional derivative, df to du, is maximal. The direction in which df to du is maximal is precisely the direction in which this is maximal. Do you agree? For C1 functions, for smooth functions, for which this is maximal. Now this is fixed. You're standing at a point, the gradient is fixed, right? So the only thing that can vary is the direction, right? So when is this scalar product gonna be maximal? What is this scalar product? It's the gradient of f, its length, times the length of u, times cosine of theta, where theta is the angle between the two, right? Doesn't this remind you of the old days, right? Remember we discussed these things years ago? Yeah? Everybody remember this, right? That's the definition of the dot product. What's this thing? This is 1. U hat. It's a unit vector. So this is 1. This is fixed at a given point. So when is the directional derivative maximal? When this is maximal. What's the maximal value cosine theta could be? 1. Okay. So df to du is maximal. And when is cosine theta 1? For which angle is cosine theta 1? 0. For the 0 angle. So df to du is maximal when the angle between these two is 0. What does it mean that the angle between two vectors is 0? That they're pointing in the same direction. Okay? So df to du is maximal when u is in the direction of the gradient. So you're standing at a point, standing mathematically at a point. If you're standing there physically, you can just look and see which direction looks steepest. But if you're mathematically standing at a point on a graph of a function and you want to know in which direction is the directional derivative biggest, the steepest slope, the direction of the gradient. Okay? And that in fact is used in everyday language, right? People say, what's the gradient? The gradient, the slope at a point. Clear? Everybody good? Okay. And exactly along these lines, when is the f to du minimal? So when is this expression minimal? When cosine is -1. Cosine is -1 when theta is pi, right? Which just means that the gradient is pointing in the opposite direction of u. Okay? So the f to du is minimal when u is in the opposite. Double P? Direction of the gradient. Clear? And finally, the question is about level curves. When is the f to du equal 0? When are we walking along a level curve? Walking along a level curve means that the directional derivative in whatever direction we're walking is 0, no slope. That's a level curve. When is it 0? When this is 0. When is this 0? When this is 0. When is this 0? When cosine theta is 0. And when does that happen? When theta is pi over 2. Which means that the gradient is perpendicular to the direction. So the f to du is 0 when u is perpendicular to the gradient. So this gradient actually has a lot of geometric information hidden inside it. Okay? It tells you precisely, if you know the direction of the gradient, you know exactly where the steepest slope is. You know that in the opposite direction, it's the steepest slope downwards. And you know that in perpendicular directions are those level curves. Okay? Clear? Let me draw this, so a picture. And it's important, many people get confused because they think that the gradient lies on the graph. But that's not true. Okay? At every point xy is a point in the domain. Okay? The graph is up here. Does everybody understand what I'm doing now? Okay? If ever I do things and you don't understand, stop me. Say, hey, what are you doing? Okay? So at every point xy for a two-variable function, the graph lives up here. This is the mountain range. Okay? The gradient lives on the plane. It gives you directions on the plane. At every point, you get a direction. At every point in R2, you get a vector in R2. Okay? But that direction, if you plot it on the map, that direction is the direction in which, when you look up on the graph, if you go in that direction, you would be taking the steepest route to the summit. Clear? Okay? So that's what I want to draw now. I'll do my best. You know, you open a book, you probably find better drawings. But, so, tell me what I'm drawing. So what are these? Right, so this is the topographic map. This is an aerial view of the xy plane, of the domain. Okay? And these are the level curves. Here's the summit, maybe up here. And suppose I'm starting my journey down here, or down here. Okay? At every point on the xy plane, the gradient is going to be a vector pointing at the steepest direction upwards and perpendicular to the level curve. Clear? So this is going to be the gradient at this point, and this is going to be the gradient at this point. And if you want to find the shortest route in terms of distance to the top, just follow the gradient. Okay? So at this point, it's going to be like this. Okay, and then you're saying, hey, that's not pointing at the top. No, but this is the shortest route. And here there's another level curve. And when you get to this point, okay, there are more level curves, right? Every point is a level curve. So you get to this point, it's already going to point here because it's perpendicular. And when you get to this point, it's going to point here. And if you follow the gradient, that's the shortest route to the top in terms of distance, in terms of taking just the steepest slope. Okay? So if I now take this, so this is the aerial view. I'm a satellite now. And now if I take it, you know Google Earth? Isn't that wonderful? Okay, so you take it and you press, I don't know, do this, and you get it in a side view. Doesn't always do it good, but sometimes. What you would see is what? Is a mountain whose peak is here. So you'd see something that looks like, maybe like this, kind of steep here, more, right? This is what you'd see in a side view. Do you agree? And these level curves are now on the mountain. Well, they're not there in Google Earth any longer, but if you imagine them, they're going to be like this, right? So do you agree that this is a side view of the same phenomenon? Can you see the gradient here? No, the gradient lives on the plane. Okay, you can't see the gradient, but you could see, for example, if you want to trace the line it would take, trace the trail or the road it would take. So what we started from somewhere down here, and the road it took us along would be something maybe like this, all the way up to the top. Yay. Clear? Everybody? Okay. So this is the geometric meaning of the gradient. We only discussed the gradient so far for two variable functions. So for f of xy, the gradient is df to dx, df to dy. When you have a three variable function, the gradient is going to be df to dy, df to dx, df to dx, df to dy, df to dz. And can you guess what the geometric interpretation of the gradient would be? So here the gradient was perpendicular to the level curves. For three-dimensional functions, the gradient is going to be perpendicular to level surfaces. Okay? And arguing that is a bit more complicated, and we will do it, but a bit later on. Okay? We're going to reason it out and figure it out a bit later on. Okay? That the gradient for f of x, y, z is perpendicular to level surfaces of the function. Okay, it's the normal to the level surfaces. Okay, so I guess this wraps up this discussion. We'll see many examples in tutorial, in your homework, and as we go along.